the second half of the class deals with sampling distribution. We talked about a population is the group that we're interested in learning about, and the sample is a subgroup of the interested population. And it's a finite group, it's a limited number of people, and it must be random. And then I did the analogy of the dice, where if you know something about the entire population, that allows you to make a theoretical conclusion about your sample. Here's what I think will happen in my sample. But if you're taking a sample and you're trying to make a conclusion about the population, it's not actually a conclusion, it's just a prediction that may have error involved. So the second half of the year is how to use sampling methods to make predictions about population and be able to calculate the amount of error in your prediction based on your sample size. Because if you can calculate your prediction and calculate your error, that allows you to give a window of results. So here's where, I don't know exactly where the answer is, but I'm pretty sure the answer is between A and B. Okay, so that's what we're talking about. So just a quick overview of sampling, the aims of sampling, the benefits of sampling. First of all, you can make generalizations. You make generalizations about the population. Make generalizations about the population. You can say, from our sample, here's what we think should happen with the population. But another main reason of sampling, another aim of sampling is it reduces the cost of research. Reduces the cost of research. If you want to know about how many deer in the state of Ohio are infected with Lyme's disease, you can't collect every single deer in the state of Ohio, so you go out and you collect a sample of, say, 1,000 deer, and based on the percentage of the deers that have Lyme's disease from that 1,000, that allows you to make a prediction about the entire state. Does that make sense to everybody?
If a deer has Lyme disease, can you get it taken?
I'm not for sure. I would assume yes.
Yeah.
All right, so what we're going to start off talking about is categorical data. So just like we, at the beginning of the year, we talked about categorical, and then we're going to talk about quantitative. We're going to start off sampling distribution with categorical data. What is categorical data? Anybody?
Yes.
Data that can be arranged.
Something that's not a number. Something that is not, well, it can be a number,
It's like
but it has to be a number that does not hold a place value, or it has to be some kind of group ownership, right? So if we're talking about the deer having Lyme's disease, it's either a deer with Lyme disease or it's a deer without Lyme disease. Does that make sense?
Yeah.
Or if we're talking about party that you belong to in terms of a political party, Democrat, Republican, Independent. That's categorical data. We can also, what we're going to talk about in terms of sampling distribution more so is we're going to talk about success and failure. Success and failure. So if we're trying to do a research on how many deer in the state of Ohio have Lyme's disease, we collect a sample of deer and we have the success, if we're studying deer that have Lyme disease, the success would be a deer that actually does have that. I mean, that's not something, that's not a favorable thing. You don't want them to have Lyme disease. But in terms of a study, having a deer that has Lyme disease is considered a success in terms of that study. Okay, so we're breaking it up into success and failure. Either you have this, you don't have this. Your answer is yes to the question, your answer is no to the question. Now, what about Republican, Democrat, Independent? How can that be just success, failure? If their options are Democrat, Republican, Independent, how can we turn that into a success, failure?
Either one and two then.
Well, in terms of, like if I said party ownership, what party do you belong to? How can I turn that into just success or failure?
Couldn't you do your
Okay, so how many people are in the Republican Party versus everyone else? So what we could say is a success, for example, Republican, A success would be being Republican. A failure would be not being a Republican. So your successes would be all of your Republican voters or candidates. Your failures would be the combination of Democrats and independents. Does that make sense to everybody? So we're looking at data in terms of just belonging to two groups, success or failure. Now, when we're talking about that, we can talk about it in terms of proportions. Proportions, right? Part to whole. If we ask 10 people, what party do you belong to, and 3 of them are Democrat, we can say that the proportion of people that are Democrat were 3 out of 10, 3/10, right? So we can talk about proportions. Proportions can also be talked about as probabilities. Okay, proportions, probability, percent, all of these can be interchangeable. What's the percent of your data that was Republicans? 3 out of 10 is a proportion. We can also think of that as probability, which we'll get to in just a second. Or we can think of that as percent. 30% was Democrat, right? The probability. So let's just do a real quick recap of probability. Probability is the chance of something occurring. The chance of something occurring, and we can write it like this. P of S can be read as the probability of success. Probability of success. So if we're talking about flipping a quarter and we want to say how many heads are there, we can write that as the probability of landing on a head. Now what's the theoretical probability of flipping a quarter? What's the theoretical probability of heads? 1/2. Now if you were to flip it 100 times, does that mean 50 of those times will be heads? No, the experimental probability will not be the same necessarily. It can be. But anyways, the formula for probability of success is the number of successful outcomes over the number of total outcomes. If we flip a coin 100 times and it lands on heads 52 times, then it was successful 52 times out of the total 100 times that it's been flipped. Does that make sense, everybody?
Yes.
All right, so with that said, that gives us a limit of all our probabilities. Your probability is always going to be some kind of number that never exceeds what?
100.
1, right? If you're to flip a coin 100 times, the most times you could get a heads is 100. So the very best thing that could happen would be 100 out of 100, which reduces to 1. So probability is at most 1, and which means 100% guaranteed it will always happen.
At least 0.
Or at the very least, 0. At the very least, 0. 0 successful outcomes out of the total. You can never have a negative probability. So what we can write like this is probabilities always fall being less than 1 and more than 0. So that means probabilities are either going to be written as fractions or decimals. Does that make sense to everybody? If you were to say 100, if you were to say 100, that means it's, the probability of something happening is not 100. The chances of it happening is 100 what? Percent. Okay? So, let's maybe a good recap is, okay, we put 5 marbles in a bag. 3 are red. Five marbles in a bag. Turn your phone off. You can say just ignore the phone call.
I turned it off. It's not mine.
Someone else turn your phone off. Sorry, Hannah.
It's not mine. It's off.
Okay. 5 marbles in a bag. 3 are red. Okay. As a proportion, if the question asks you what proportion are red, what's the answer?
3 out of 5.
3 out of 5. Proportion are red. 3 out of 5. We can write it as this. We can write it as 3 out of 5. Or we can write it as a ratio. Those are all ways to write proportions. Now, if we're talking about a probability, which could be written like this: the probability of red, or we could just write it as the probability of, if there's only one color that starts with an R, you can just put P of R, probability of red. We can either say 3 out of 5, or we can say 0.6. If it asks for a probability, it's either going to be a fraction or a decimal that's between 0 and 1.
Hey, Mr. Cameron, I also heard like when they say 3 out of 5, I also heard like 3 to 5.
3 out of 5, 3 to 5, that works also. Yeah.
You write a different color.
Sure. Percent red, I'll just start after this one, would be 60%.
Now write with the red marker says Christmas first.
Yeah.
All right. Percent red would be 60%. They all mean the same thing. They're all in different contexts. Proportions is strictly 3 to 5, or 3 out of 5, or 3/5. Probability can be 3/5, 4.6. Percent is 60%. Okay? But they all apply the same thing. All right, so let's take a look at this. Here's a note. This is a survey conducted in May of 2007. This is a survey conducted in May of 2007. It was conducted by the company known as Galleys. This is called a Galleys poll. They're a business that's hot. They're a company that's hired to conduct surveys and take data. So this is a Galleys poll. They contacted 1,000 U.S. adults, 1,007 U.S. adults. And they reported that 43% believe in evolution. They say 43% believe in evolution. All right. It doesn't give the context of what they define as being evolution. It doesn't say if they give a description to the person they're asking of what they mean by evolution, because a lot of people have misconceptions of what evolution means, right? So varying ideas of the definition of evolution. But they just say, do you believe in evolution? They get a 43% yes. Okay. Now, Baylor's religion survey also does the same kind of survey. Calls U.S. adults. They call 1,584 adults, or contact 1,584 U.S. adults. And they get 668 believe in evolution. Now this is actually data that's not important. Okay. These are actual examples. This is actually, you can probably Google Baylor Religion Survey about evolution 2007 and you can probably find the actual full-blown survey. So these two were both conducted in 2007. They both get two different results. They both report them differently. So they've asked the 1007, 1584, they've asked two completely different samples. The chances of them calling the same people in the entire United States to where someone is actually included in both polls is very unlikely, right, with the number of people that are United States citizens. They both report their results. When you look at that, I mean, it's up to the reader. Which one seems better? Which one's, all right, I guess, let's take the stamp. Now, don't go home and say, Mr. McCann's promoting evolution or Mr. McCann's promoting religion. This is not the point of this. If you're taking the standpoint of, I'm a religious person, when you read that, which one seems as better results?
Okay, with the second one.
I want to say,
The Gaylor is one.
I want to
Second
say
one.
Galleys.
Gaylor.
From a proportionate standpoint,
Maybe
kind of seems like
Baylor's is better.
Baylor's technically is better,
it
but I
is.
think Galleys looks better.
It
Because
does. Okay.
if you look at it, you think that's almost half of the people.
Okay, yeah, so this is,
It's easier to picture on a pie chart.
yeah, I mean, when you look at this, you say 668 out of 1,584. I mean, the way I see it is hey, that's not that much compared to the total. Maybe. 43% is I know that's 4/10. That's a chunk of a pie. So it's all about how you word it. But inevitably, if you compare these two, has anyone figured it up yet? It's 42.1. This is 42.17%. So even though they asked completely different people, they got inevitably almost the exact same result. Does that make sense to everybody? So it's how you report it to where whatever suits your needs of how you want to make it look. Now, maybe if you're wanting to persuade, you might, instead of saying 43% of people believe in evolution, you might say 57% do not believe. And that might look better than 43 believe. Okay, it's all about using the numbers to make it look in the benefit of what you want it to say. We went to the bodies exhibit a couple years ago when it was at the museum center, and they had these statistical facts laying around the room. They would post them around the room about health. And one of them was 40% of people who died from colon cancer are morbidly obese.
So does that mean it's better to be morbidly obese? Because like a lot, like there are more people who are.
Yeah, so well, they make it count. 40% of deaths by colon cancer are morbidly obese. So when you read that, you would think, okay, that's they're trying to word it to where it sounds like you need to be healthy. But you can also read this as 60% of people who die from colon cancer are
Healthy.
not morbidly obese. So in terms of colon cancer, you're better to be morbidly obese. Okay? But they worded it to where the average person who reads it, they don't think into it. It seems like it's a persuasion on you need to be fit. But actually, it's just a play on the words in terms of the actual statement. If you reword it to where it says actually being skinny is a bad thing. So I'm, once again, not supporting either statement. I'm just saying
Just like, I think
how
like
you
lots of
choose to word your results can affect the interpretation.
Well, Mr. McCann said the cancer's a good thing.
So, okay, so this is 43%, right? What is that as a probability?
43 out of
0.43, or we can write it as 43 out of 100. If we want to write it as a proportion, we don't say 43 out of 100 because we know exactly how many there were. We would take 0.43 and times it by what? 1,007, and we get, anybody?
433.1.
433.1? Okay, so probably we would say 433 of 1,007. So now we've just taken how they reported it, and we've written it in a different way that allows it to be compared to the same format in which the other survey reported their results. So now looking at this group, they have 668 of 1,584. That's a proportion. We can write that as a probability by dividing the two. What's 668 divided by 1,584? 0.4217. What's after the 7?
1.
Okay, so that 1 would not cause that 7 to get rounded up, right? So as a probability, that could be 0.4217, and then as a percent, that'd be 42.17%. So we've got two different survey companies. They've asked two completely different samples. They've asked actually two different size samples. The samples aren't even the same size, but inevitably they got the almost exact same result. Okay, and that's the whole point of sampling distribution is you can look at a sample and make the prediction. And inevitably, if you want to make a more accurate prediction, you just keep collecting more samples. Because now you can take these two samples and average them to get a more accurate prediction. Does that make sense to everybody? Okay, so some things to go over.
Wait, Mr. Pin.
Yes.
So therefore, if you said like, since not a single person would be in the same exact survey.
Not necessarily.
Well, I mean, but you said rare.
It is rare.
So therefore, could you add those two and divide by add the two?
You technically could, but once again, doing that is dependent upon the fact that no one was repeated.
All right. Okay.
Because if there was repeat people in most surveys, you can't use that technique.
All right.
But the chances that when you're talking about how many total citizens there are in the United States, the chances that these two surveys contact the same people is very slim.
But is one
Those dang religious people keep contacting.
Do what?
Would one of these two be in a different place?
Region?
Yeah.
It could be. It could be a nationwide. Most likely, it's a nationwide survey. Because when you survey something about an entire nation, you don't want to look at just one region. Because if you look at just the Northeast, you're getting Northeast opinion. You're not getting a nation opinion. Northeast opinion about mudslides or Northeast opinion about tornadoes is not going to be the same as someone asked out in California about mudslides or someone else's opinion about tornadoes in the Tornado Alley, yeah, out west. Does that make sense? So where you're at depends on your opinion of situations.
Do you remember when Tornado Alley was in Ohio?
I don't remember.
That was, I didn't think so. Okay.
No, I don't remember. Okay.
Okay. Like, it was like in, like 19, what does that sound?
Okay.
Sorry.
So, the population proportion. We're going to denote that with the letter P. Proportion is the number of successes out of the total, right? The population proportion is the proportion of the entire population. Who commit a success. The proportion of the entire population who commit a success. Unless you were to, if you were wanting to talk about the number of Democrats in the United States, the only way to know the population proportion, how many people there are actually in the United States that are Democrats, would be to contact every single person in the United States. Does that make sense to everybody? So the population proportion is almost impossible to figure out. Now, if we asked how many students feel that the school lunch is not a very good school lunch in West Union High School, that's not out of the grasp of getting an answer to, because you're asking 600 students rather than millions of people. But we also have what's called a sample proportion. Does our sample proportion, this is the proportion of successes in our sample. This is the proportion of successes in our sample. Does that directly reflect the entire population? No. There's error involved, correct? So if you have a sample proportion, it doesn't directly relate to the population's proportion. There's error involved. The sample proportion is only a what? It is a percent of the population, but the sample proportion, it's a way of making a estimation, a guess, a prediction. What symbol did we use for predicting y values? The y hat. So the notation for sample proportion is it's a p, it's a proportion, but it's going to be p hat. It's a predicted proportion. We don't know the entire population, but we're predicting it from our sample. So it's a predicted proportion.
That view looks like a mind on that. That looks like my back.
Okay, so how much time we got left before I get too far into this?
20 minutes.
Okay, 20 minutes. All right. Benefits of. All right, let's go over sampling distribution.
Camera.
Sir? Sampling distribution. Sampling distribution is looking at repeated samples from an entire population and interpreting the combined results of all samples to predict the population. Looking at repeated samples, typically of the same size. Looking at repeated samples, typically of the same size. Looking at repeated samples from an entire population and interpreting the combined results of all samples to predict the population. Okay, so if we want to know about something about the entire United States, how many people are Democratic? If we go and we ask 30 people, can we use that 30 people to make a prediction?
No. Yeah, but like it's going to be very weak.
Yes, but it's going to be very weak, right? Because 30 people in comparison to the entire nation is not that much of the entire population. But if we were to go ask another 30 people and look at just that information,
Like it's slightly.
we've now got two samples of the same size that we can combine to make a stronger sample. Does that make sense?
Yes.
So if we continuously do that a bunch of times, so if we go ask 30 people and we find the answer to that, and then we go look at and we do the repeat that say 50, 60 times, we're not just getting one group of 30 people's opinion, we're getting 50 to 60 groups of 30 people's opinion. Does that make sense? So the strength of our study for every sample we increase, for each number of sample that we increase is going to get stronger. So we're looking at repeated samples, looking at the same kind of sample over and over from an entire population and interpreting the combined results of those as a prediction for the entire population. That's what that's saying. Here's the benefits. And let's just talk about the benefits in terms of, let's just do a quantitative example. Here's a very easy way to benefit, a benefit of this kind of a concept in terms of a quantitative example. And the example that we're going to do is income. Income is an example of some kind of data that we would collect where the sampling distribution, repeating the same kind of a sample over and over and over again, is going to be beneficial to making a prediction. Earlier in the year, we talked about if you were to collect everywhere, if you were to collect a population's income, no matter where you go, the NFL, Adams County, the state of New York, the state of California, it's always going to be a what kind of histogram? It's always going to be a skewed histogram. So if we were to look at income, is it positively or negatively? Positively, right? It's always going to be a lot of people make a little money. There's a few people that make a lot of money. That's going to hold true no matter what profession you look at. If you go look at doctors, the majority of doctors are going to make a little bit of money. There's going to be a few doctors that do an exceptional job that make a lot of money. So income is always going to be skewed.
Like Dr. Phil.
So if we look at the average of this, the average is going to chase the outliers. The average is going to chase the outliers, but it's going to be skewed. So the dilemma arises, can we use the empirical rule to talk about it?
No.
No, because the empirical rule is dependent upon the data being what kind of data?
No.
Normal. Does that make sense? So although we've collected data, we've got results, we can't do anything with them because it doesn't fall into the assumption that it has to be normal data. So what we say is, okay, let's record this piece of information. So we're going to record this average. Okay, so that's sample 1. So we'll call this sample 1. Now, if you go out and you collect another sample, is the curve going to be the exact same curve?
No.
No. If you change samples, the curve's going to change a little bit. The chances of it being the exact same curve, having the exact same results is very, very unlikely. But even if you ask a whole other group of 30 people, the histogram still is going to be what kind of shape? It's still going to be skewed. So we'll call this X bar 2, our second average. Okay? Once again, we can't do anything with this because we have skewed data. In order to talk about the empirical rule or anything that deals with z-scores or p-values, we have to have normal data. All right, so we go out and collect the third sample. It might look like this. It might have a slightly different shape, and that's okay. But overall, the shape is still going to be skewed. So we're going to have a third average. Can't do anything with this. If we repeat this process, n times, typically n is more than or equal to 30. In order to do sampling distribution, you need to collect this kind of a concept. You would need to do this 30 times. Select a sample of people, and you would need to repeat that process 30 times. You're going to have 30 different samples that are all what kind of shape? Positively skewed. But each of those samples is going to have a mean. Does that make sense to everybody?
Yeah.
So even though we're going to have 30 samples, okay, so at the end of this, we have at least, because you need to do it more than or equal to, at least 30 samples, all skewed. We have at least 30 samples. They will all be skewed. That's always going to happen. You will never collect data if you collect it correctly. If you collect it randomly, you will never have data about income that is not skewed. So we have at least 30 samples. They will all be skewed. We take the mean of each sample. If we look at just the mean of each sample, how many means are we going to have now? We're going to have a total of, giving us a total of 30 means. Right? So we're going to have 30 X bars. Now here's the benefit of doing this. We conduct a survey, we ask for their income, we do this a bunch of times. Every single time we do it, we get skewed data, but we take those 30 means. And then we do a data analysis of just the mean of each sample. If we do a data analysis of those 30 means, the data analysis that will result in a normal distribution. Does that make sense to everybody? Because we're not looking at the raw data, we're taking just the mean of the raw data and comparing all of the means of each sample's raw data. So the result of this is the distribution of these 30 means will always be normal.
Always.
Always. As long as you do it more than 30 times.
What if you do it
It's a rule that will actually, it's a rule that's been proven and we'll actually write it down later.
Why would we not use median?
You can. This rule holds true for any kind of quantitative variable. So we could have looked at the median of each sample. And then the 30 medians combined would make a normal distribution curve. So you could actually have a normal distribution curve for the medians. You'd also have a normal distribution curve for the means.
That's what we represent that.
Yeah, well you can, and that's what we will do. And then you can also do the, you have normal distribution for the mode. Yeah, it'll all end up being normal distribution, no matter what quantitative variable. As long as it's a quantitative variable you look at, it'll always result in a normal distribution. Okay, with the very lowest point on the curve being the smallest average, right, that we found in all of our samples, and the highest point in our curve being the largest average we found in our 30 samples, 30 or more samples. Okay. All right, so that's the benefit of sampling distribution, and now we're going to go into the concept of sampling distribution using analyzing categorical data. Analyzing categorical data. Okay, so I gave a benefit of, here's where this is beneficial in terms of quantitative because it makes the most sense. But if we're looking at categorical data, we're talking about group ownership. When we're talking about group ownership, belonging or group belonging to Democrat, Republican, belonging to smoker, non-smoker, alcoholic, non-alcoholic, whatever it may be, blue-eyed, brown, not blue-eyed. There's not a numerical value attached to that. It's either yes, I am a part of this group, or no, I'm not part of this group, right? So in terms of analyzing categorical data, what we have to use is we have to use probabilities. We must use probabilities or proportions. Probabilities / proportions. They're inevitably the exact same. So we can't say, to interpret our results of a study, you would have to say this percent or this out of this many people, this many were blue-eyed. We have to use a probability or a proportion. If we know the population proportion, P, if we know the population proportion, the P, what the entire population's actual true proportion is, we can test the accuracy of our sample proportion. We'll call that, and then of course that's P hat. So what's this saying? If we know the population proportion, if you know that 40% of students at West Union High School cannot stand the school lunch, and you go collect data and you say, wait a minute, I found that 60% of people cannot stand the school lunch. And that means one of two things. Either A, the population proportion is wrong, which is harder to prove than the sample, right? If your one study cannot disprove the entire population. Well, what that could lead into is when you say, well, wait a minute, I got drastically different results than the actual population. Therefore, maybe I made a mistake in doing my study. Okay, for you to get drastically different results than the entire population, then there must have been some kind of flaw in your study. Okay, and so to do this, we find a 95% confidence interval for P. We find a 95% confidence interval for P. So what we're going to do is we're going to say, based on what P is, we don't know what our sample should be, but we can be 95% confident that it's between these two values. Does that make sense, everybody? And the way we do that is, what did the empirical rule say 95% of the data was between?
2 standard deviations.
2 standard deviations below and 2 standard deviations above. So we're going to apply that same concept. It's not called a standard deviation, it's called something a little bit different. It's called standard error. We'll talk about that more tomorrow. But we're going to find out how to calculate standard error below and standard error above P. And then from that, make a prediction of here's where our samples should be. And we'll stop here for today.